All right, so let me talk about a couple pitfalls that students often fall into. There's some tricky spots that students tend to be especially prone to making mistakes on. As I said in the intro, probability is one of these topics where you can be so confident that you have the right answer, and it just turns out you're dead wrong, and you don't even realize that you are, right? So here's a couple places where that comes in. First one is simple, but you just got to get your head around this, and for some reason students often make this mistake, and that is that they confuse the notion of independence of events with mutual exclusivity of events. Maybe those words kind of sound alike, independent and mutually exclusive, both sort of sound like, oh, they're opposites or different, not overlapping or something like that. Let me just make very clear that independent is not the same as mutually exclusive. Quite the opposite, in fact. Let's take an example here, right? Suppose I said, I want the probability that a person that I meet is pregnant. And we said, who knows what that is? Maybe that's 0.02 or something like that. So I've established P as the event that a random person that I meet in the parking lot or whatever is pregnant. Now, what is the probability that they're pregnant given that they're male? I'm saying that male people belong to the M event, right? Now, if these were truly independent of each other, then we'd say, learning that they're male gives us no further information, therefore the probability is 0.02, right? That is absolutely not the case. Obviously, the probability that they're pregnant, if they're male, is 0. So this is absolutely different than this, and that was one of our conditions for being independent, is that those two would be the same. The problem that we're falling into here is that these two events are mutually exclusive. Another way of saying that is disjoint, right? And mutually exclusive is not the same as independent. As a matter of fact, mutually exclusive events are quite dependent, right? Because if the outcome is in one of the events, then it is by definition not in the other event. That's what mutually exclusive means. If I find someone who's male, they're not pregnant. If I find someone who's pregnant, they're not male. So a lot of students will look at this and say, you can't be male and pregnant, therefore they're independent of each other. Just make sure you don't fall into that fallacy. They are absolutely not independent. They are very dependent. Mutually exclusive is the word that you want, right? All right. Second pitfall that comes up, it comes from violating another rule. So what I want to do is I want to write down 2 rules, and we've mentioned these already, but just for completeness here. Here's 2 rules you can count on. And I want to make sure you understand the circumstances in which you can apply these rules. The probability of the union of 2 events, the probability that the outcome is in either A or B or both, is going to be equal to the probability of A plus the probability of B if and only if the events are mutually exclusive or disjoint, right? That is the condition that must be satisfied for this rule to hold. The probability of the union is the sum of the probabilities only if they're mutually exclusive. Now remember, if they're not mutually exclusive, we can always bail out by saying, let's subtract off the intersection, right? We can always do this. Minus the probability that both events occur. That's so we get rid of the double counting thing here, right? So this is true always. But this is a pitfall students tend to make. They tend to apply this top rule even if the elements are not mutually exclusive. And we'll see an example of that, right? So these together sort of make rule 1. And then rule 2 I mentioned on the previous slide, but let me mention again here because it kind of is parallel. The probability of the intersection of 2 events is equal to the product of their 2 probabilities, if and only if they are independent. So this does not depend on mutual exclusivity. That depends on independence. And you can only apply Rule 2 when the events are independent. If I want to find the probability of an Asian male, I can multiply the probability of an Asian times the probability of a male, but I cannot do that with a pregnant male because the former 2 events are independent and the second 2 are not. So commit those 2 rules to memory and sort of see why they work, right? Now let me give you an example here, and here's one that just classically students get wrong. So let's start with an easy one here. I'm going to roll a die. This tends to be an example we use a lot because it's just so easy to think about. All 6 sides equally likely to come up. It's a game of chance, etc., right? So I'm going to roll 1 die. That's going to be my first little experiment. And what I want to know is, what's the probability that I get a 6? And the answer is, if it's a fair die, that's 1/6, right? 1/6 chance for each side. All right, that's easy. Now, suppose I roll 2 dice. And I want to know what is the probability of getting boxcars, right? Getting double sixes. And the answer is 1/6 times 1/6, which is going to be 1/36. And it's important that you understand the reason that this works is because these two, almost wrote mutually exclusive. Because these two events are independent of each other. And when I say the two events, what I mean is the fact that I do or don't get a 6 on the first one has nothing to do with the fact that I will or will not get a 6 on the second one. And that's an assumption, right? If the die has memory or something, then that might not be true. But we're going to assume that every time I roll the die, it's sort of fresh, starting over. I jiggle it up enough in my hand that it's not going to, have any effect from one roll to the next, and therefore they're independent. And that is the only reason I can do that product there. I could not do that product if they weren't independent. So that's an assumption, and that turns out to be true. Now here's the one that really messes people up. Suppose I roll 2 dice, and I ask, what's the probability that I get at least 1/6? Because maybe that's a bet that I've made with my friend, right? Can I roll at least 1/6, Okay, here's the fallacy. A lot of students will say, well, the probability of getting a 6 if I roll once is going to be 1/6. So clearly the probability that I get at least 1 is going to be 1/6 plus 1/6, right? I mean, after all, I get 2 chances. I can either get a 6 on the first one, and if that doesn't work out, oh well, too sad. I still get a second chance to roll, right? And this seems perfectly logical. It just seems like the right answer, right? Turns out this is totally wrong. Let's see why it's wrong. First thing I would do, before I tell you what the right answer is and lead you towards that, is I would encourage you to think it through sort of in the extremes, right? Here's why this is hard, and it's easy to fall into this trap. Because 1/6 plus 1/6 turns out to be 1/3, right? And that is about right. That's in the ballpark, right? And so that's why it's easy to look at this and say, great, I got the right answer, move on to the next question of my homework or whatever. Without thinking through, does this logic truly apply? And here's how you can see that it doesn't apply. What if I said you're going to roll 3 dice, and I want to know what the probability of at least 1/6 is? Well, by that logic that we had before, I would say, well, it's 1/6 plus 1/6 plus 1/6. That's going to end up equaling 1/2. Now, again, you don't necessarily smell a rat yet until you start thinking through. What if I roll 4 dice? What if I roll 5 dice? What if I get to roll 6 times and I want the probability of at least 1? Here's where you should start to smell a rat. Because if you work that out by the same logic, you're going to get 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6. That's what that logic would tell you, which is going to be equal to 1. Now, can that possibly be true? Can this possibly say that if I roll a die 6 times, I am guaranteed beyond the shadow of a doubt that I'm going to get at least 1/6? Certainly that's not the case. If you roll a dice a couple minutes again and again, you're going to have lots of strings of 6 or more rolls where there weren't any 6s. Clearly, it can't be the case that there's a 100% chance of getting that. And if you're still not convinced, what if you roll 7 dice? Let's use this same logic. Is the probability of at least 1 going to be 1/6 plus 1/6 plus ... plus 1/6 7 times? That would be equal to 7/6, which is going to be 1 and a 6, right? That's borked, man. That isn't even a valid probability. That's over 1. So clearly this reasoning is messed up. And what you have to realize is that you have made a fallacy here. And what you've done is you've said the probability of at least 1/6 when you roll 2 dice is 1/6 plus 1/6. This is wrong because you assumed that those 2 events were mutually exclusive. And those 2 events are not mutually exclusive. They are not mutually exclusive because it's certainly possible to roll a 6 on the first die and also roll a 6 on the second die, right? That's certainly possible. And so what we'd have to do is say, subtract off the intersection, right? We're going to have to say, what's the probability of getting at least 1/6? Well, the probability is going to be 1/6 that's the probability of getting a 6 on the first die, plus a 1/6, that's the probability of getting a 6 on the second die, minus 1/36, because that is the probability of getting double sixes. And if I roll double sixes, then that means my outcome was in both events. It was in that one and in that one. And the reason I got the wrong answer before was I was double counting that. I was basically saying a double 6 counts as getting at least 1/6. Oh, but it also counts as getting at least 1/6 again. And that's what gave me erroneously 1/6 plus 1/6 is my answer. Okay, so just for completeness here, there's at least 3 ways to work this out, all of which give the same answer. So, one way is subtract off the intersection appropriately. And the reason I have to do that is because these events are not independent. Not mutually exclusive. I meant to say, sorry, not mutually exclusive. So the probability of A union B is always equal to the probability of A plus the probability of B minus the probability of A intersect B. And so if we say 1/6 plus 1/6 minus 1/36, then we're going to end up getting the right answer, which ends up, by the way, being 11/36, right? If I do my math here and I say 1/6 is the same as 6/36s, and if I say 1/6 is the same as 6/36s, I'm just multiplying numerator and denominator by 6, and then I subtract from 36, then that gives me 6 plus 6 minus 1, that's what I wasn't doing before, over 36, which equals 11/36. Okay, so that's one way to get it. We have violated our assumption, therefore we have to make sure that we subtract off the intersection. All right, another way to get this same thing is to simply count all the outcomes. Now this way is a little bit easier and more tedious though. So let's list all the outcomes. If I roll 2 dice, I could get a 1 and a 1, I could get a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, or a 1 and a 6. Or I could get a 2 then a 1, a 2 and a 2, a 2 and a 3, a 2 and a 4, a 2 and a 5, a 2 and a 6. Yes, I am going to write all these out. 3 and a 1, 3 and a 2, 3 and a 3, 3 and a 4, 3 and a 5, 3 and a 6, 4 and a 1, 4 and a 2, 4 and a 3, 4 and a 4, 4 and a 5, 4 and a 6, 5 and a 1, 5 and a 2, 5 and a 3, 5 and a 4, 5 and a 5, 5 and a 6, and then 6 and a 1, 6 and a 2, 6 and a 3, 6 and a 4, 6 and a 5, 6 and a 6, right? All those possibilities are our 36 total possible outcomes, right? Now, if I want to figure out what is the probability of at least 1/6 coming up, all I have to do, since each of these is equally likely, is take the number of outcomes that have at least 1/6 and divide it by 36. So the question is, how many have at least 1/6? And the answer is, I have got that one, that one, that one, that one, that one, and all those, right? Those are all of the outcomes that have at least 1/6, and if you count them, you will see there is 11 of them, not 10. And again, that's because this guy is only one outcome, right? It's true that if I roll double sixes, I do win the bet with my friend. It counts as having rolled at least 1/6, but it doesn't double count, right? It's still only getting at least 1/6 once. And that's the reason that we overcounted before, is because we were ending up counting that twice. All right, so that's the second way to figure it out. If that's easier on your brain, then that gives you that one. Here's a third way, and this is kind of a trick, and that is compute the probability of the complement of the event, right? Because we remember the probability of A is equal 1 minus the probability of the complement of A. That's just the nature of how probability measures work, right? Because everything has to add up to 100%. So if I have a 36% chance of getting some event, that means I have a 64% chance of not getting the event, right? So I could say that the probability of at least 1/6 is equal to is 1 minus the probability of not getting at least 1/6, right? So no sixes. So then we ask ourselves the question, what is the probability of getting no sixes? And the answer is, I have to roll a non-6 on the first die, and there's a 5/6 chance of getting anything except a 6 on the first die, and then I'm going to multiply that by 5/6 on the second die. Why am I allowed to multiply there? Because these two events are independent. Rolling the first die and not getting a 6 has nothing to do with rolling the second die and not getting a 6. There's no influence there at all. Therefore, I can multiply those two probabilities together, and that gives me the probability of not getting any 6s. And if I multiply this out, I get 25/36. So my total answer here ends up being 1 minus 25/36, which is the same as 36/36 minus 25/36, which is the same as 36 minus 25 over 36, which ends up being 11/36. QED, bada boom, ends up working, right? So that gives us a really good sanity check. There were sort of 3 different logical methods that we use to compute the probability of getting at least 1 6. They all ended up with the same answer. So, not sure what to tell you except be careful, right? It's very easy to fall into these fallacies, and I think just the key to getting it right is sort of thinking it through in a couple different ways and making sure that your logic holds. Don't jump to any conclusions about what the probability is without saying, now, does that make sense when I kind of take it to its logical conclusion? And again, that's the reason that you can kind of sound the alarm on that just adding 1/6 to 1/6 thing, because it violates one of the assumptions that we have. And clearly that's not going to give you the right answer.